So here we go. So we're going to start on E2 selectivity. Right? We had talked about how when you're doing an E2 reaction, you can simply label alpha, beta 1, and beta 2, right? And if you have two different beta carbons, how do you know which one you're going to make your double bond to, right? The general rule of thumb is you want to make the most stable double bond possible, right? And that is most of the time the most substituted double bond, right? So we want to make the most substituted double bond, right? And this goes back to Zaitsev's rule, which we'll touch on here in a second. But why? Why do we want to make the most stable double bond, right? So the E2 reaction transition state looks like a double bond. So, right, if we think about our mechanism, right, it's one step. We have our base, grabs the hydrogen, electrons come over, right? But the transition state has a partial double bond in it. Right, so we're starting to form our double bond. And the more substituted the double bond, the more stable it is. So our transition state has a double bond in it, right? Oops, we're going to fit it in there. Oops. So a more stable double bond means a lower energy transition state, right? So it's just easier for the reaction to make the more stable double bond because the transition state that you have to go through is lower in energy. So if you remember everyone's favorite reaction coordinate diagrams, right? So let's say here's our double bond, or here's our starting material, right? Like right there. We have a reaction that goes up, comes down, and makes our more stable double bond, right? And if we make our less stable double bond, our less substituted double bond, our transition state is going to be higher in energy. So if you remember, the lower the activation energy, the faster the reaction. So the orange activation energy, the one that leads to the more stable double bond, the more substituted double bond, is lower in energy than the activation barrier that leads to the less stable and less substituted double bond. So if given a choice, the molecule is going to go the path of least resistance. It's going to go the path that has the lowest activation energy to lead to the product. So the reason it picks the most stable double bond is because that's the double bond that forms fastest because it has the lowest activation energy. Right? As you know, Zaitsev's rule says that we need to make the most substituted double bond possible. Right, and we do that by removing a beta carbon from, remove a hydrogen, not an, a hydrogen from the most substituted beta carbon. Right. So you remove your hydrogen from the beta carbon that is most substituted, and that's just the one that has the least number of hydrogens on it already. All right. So, right, our kind of first example, right, you have your alpha, beta 1, beta 2. Beta 1 has 3 hydrogens, beta 2 has 2 hydrogens. So you're going to make your double bond towards beta 2. And that's going to be the product that you expect. All right, if you have more beta carbons, that's fine. We're going to do the same thing. We're going to find your alpha carbon, then all of your beta carbons. So where are we going to make our double bond to? Beta 1. Beta 1 has 1 hydrogen. Beta 2 has 2. Beta 3 has 3. So we're going to make our double bond towards beta 1. Right. And there's another thing we need to think about for E2 reactions, and that's the type of halide. More substituted halides lead to more substituted double bonds. Right? So what that means is that if we have a tertiary halide, this is the fastest type of halide for an E2, right? Because it already has 2 groups on the carbon that has the halide. So you're going to make a more substituted double bond than if you had a secondary halide. Right, so the example I have drawn, the tertiary one leads to a tri-substituted double bond. The secondary bromide leads to a di-substituted double bond. And then if you have a primary halide, right, that's going to lead to a mono-substituted double bond. Right, so this is going to be the slowest for E2. So the more substituents you have on your carbon that has your halide, the faster the elimination is going to be. Because you just inherently are going to end up with a more substituted and thus more stable double bond. So if you notice, this trend is exactly the opposite as SN2 reactivity, right? SN2 primary is fastest, then secondary, then tertiary. Basically doesn't happen. Here, it's the exact opposite. So we're going to follow Zaitsev's rule, except there are 3 exceptions that we need to know for E2 reactions to Zaitsev's rule. So big bases make the least substituted double bond. So I'm going to give you only 2 big bases that you need to know, just 2. So you've got potassium terbutoxide, which on your homework they often will write like CH3, 3HCOK. And then LDA. Right? These are both large bases, and they will make the least substituted double bond that they can. So they will flip on Zaitsev's rule and make the least substituted thing. So if you have, again, we have our little dumb example. If we add a big base, we're going to make the least substituted double bond. Again, I'll specify E2. Here, same thing, alpha, beta 1, beta 2, beta 3. Right? This is going to make the least substituted double bond, so I'm going to make the double bond towards beta 3. So the question then becomes, why does this happen? Why do big bases make the least substituted double bond? So big bases can't easily reach the hydrogens on the more substituted beta carbons. So, in kind of just like the most dumbed down way to think of it possible, right? If you've got your leaving group, and let's say we try to take the hydrogen from the more substituted beta carbon. If you have your base in there, right, what's going to happen is your base is going to bang into your molecule, right? If I put it on either side of that hydrogen, right, it's really big and starts to hit the molecule, right? Now, if I have it take the least substituted hydrogen, right, in this example, there's a ton of space for that base to go like stick out into the world and not bang into the molecule. So the more substituted the carbon with the hydrogen on it, the more steric interactions that the base has with the molecule. So it just becomes easier for the base to just go to whatever beta carbon has the least stuff around it and take a hydrogen from there. So it's just trying to minimize the amount of steric interaction or how much it bangs into the molecule when it goes to grab the hydrogen. Right? The next exception to Zaitsev's rule, alkyl fluorides. Alkyl fluorides make the least substituted alkene. This is the only time we use fluorine in any of these, right? And this is because alkyl fluorides go through a different transition state in an elimination than all the other leaving groups. So, right, you draw the mechanism the same, right? You've got your base, whatever it is, we'll say hydroxide, and it goes and grabs this hydrogen, right? But instead of the transition state looking like the double bond, the transition state when you have an alkyl fluoride looks more like a carbanion. right? So fluorine is an awful leaving group. And so we have to basically pull the hydrogen all the way off the molecule before the fluorine will decide to leave. So we don't get to pull the hydrogen off and start to make our double bond. We have to yank the hydrogen all the way off. Our carbon has to become basically a carbanion, has to become really negative, and then finally fluorine will leave. Right? So what matters here is not double bond stability, but carbanion stability. So, oops, I put too many letters in there. All right, so carbanion stability follows the exact opposite path as carbocation stability, which makes sense because they are the exact opposite thing. Carbocations are short electrons. Carbanions have too many electrons. So it makes sense that their stability should be flipped, right? So methyl carbanions are most stable. Then you have primary, secondary, and tertiary. So in like a practical real world sense, if you get methyl lithium on yourself, you're like, I should probably take care of that at some point. If you get imbutyl lithium on yourself, you're like, ow, 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 I should wash my hand off. Tert-butyl lithium on the end there, if you put it in a syringe and squirt the syringe out, you will shoot fire across the room. Because it is so reactive, it rips the H off of water in the air, and that reaction is so exothermic that it then sets itself on fire. So just kind of a difference in like reactivity and stability, right? So tert-butyl carbanion is less stable. So your fluoride, you're looking to make the most stable anion you can because the transition state looks like an anion. Right? And then the last thing that kind of switches Zaitsev's rule or has you ignore it is resonance. Oops. So your double bond can be conjugated, which conjugated just means, means put all the letters in your word, means that it can have resonance. That double bond is going to be more stable. So let's say you have something that looks like this. Right, I'm going to make, so I've got my alpha, beta 1, beta 2. Right? Zaitsev's rule says make your double bond to beta 2. But if I make my double bond towards beta 1, this double bond is now close enough to the pi bonds in the aromatic ring that it can be in resonance. You can draw resonance structures, right? And it's always more stable to be able to draw resonance structures than to not. So you always want to put your double bond so it's close enough to interact with other double bonds if you can. So let's say we had something like this. Right? You're going to make your double bond to beta 2 because now your double bond that you made is close enough that it can have resonance, that it can interact with the other double bond in the molecule, right? To have resonance, think it's double bond, double bond, right? So I've got a double bond, a single bond, and a double bond. Those double bonds can be in resonance now because they're close enough. So big bases are going to always make the least substituted double bond. So the potassium butoxide and LDA. Alkyl fluorides always make the least substituted double bond. And then when you already have a double bond, you want to make your new double bond so that it has resonance with it if you can. So those are the times that you're going to have to look at Zeitz's rule and think, maybe it's not right. Yeah. They can only be one single bond apart. So here, these are close enough. These are close enough that they have resonance, right? If I were to put the double bond on the more substituted carbon, now this double bond is too far away from this double bond. They can't talk, right? You have to have something where it's double bond, single bond, double bond. Now those two now you can draw a resonance structure, right, where these electrons will move, plus, minus. Right, so you have to have double bond, single bond, double bond, then you can do your resonance. That's your basic E2 stuff. So now we're going to talk about E1 reactions. Right. So E2 was our analogous reaction to SN2. E1 is our analogous reaction to SN1. So right, the E, just like before, is for elimination. The 1 is for unimolecular. Right, so it's for a transition state that only has a rate determining step that only has one molecule in its transition state. So just like in SN1, the rate determining step here is when your leaving group leaves the molecule and makes a carbocation. Right, that is our rate determining step. Right, and then your base is able to come in, grab a hydrogen, push electrons up, and make your double bond. But your base is only able to come in after you make your carbocation. Because this mechanism goes through carbocation, you have to worry about rearrangements. You can do rearrangements. You need to follow Zeitz's rule. So we're going to make the most substituted double bond that you can. So in this first one, right, alpha, beta 1, beta 2, beta 3. Beta 1 has 2 hydrogens. Beta 2 and beta 3 both have 3. So we're going to make the double bond towards beta 1. And then the next one, we have to watch out for rearrangements, right? Whenever you have a secondary halide that's going to make a carbocation, you have to be mindful that you could do a rearrangement. So the product here is going to look like this, right? You make a carbocation. Then you're like, it's secondary. Can I do a rearrangement? And in this case, you can move a hydrogen. And make a tertiary carbocation. Now, once you've got to your tertiary carbocation, you can treat that like your alpha carbon. So you can say, hey, I now know that I'm going to have here, and it's going to be one of these beta carbons, beta 1, beta 2, beta 3, that's going to make, I'm going to make my double bond towards. Now, here's where Zaitsev's rule takes over. So beta 2 has the least hydrogens on it. So that's going to be your product. Fair enough. So just like we did SN1 versus E1 versus SN2, I'm sorry, we're going to do E2 versus E1. How do you differentiate the two eliminations? Right. First, we can look at the halides. If you're just comparing E2 and E1, primary halides only do E2 reactions. Right, so you never have to worry about an E1 happening on a primary halide because you can't make the carbocation. So primary and secondary halides do both, E1 and E2. So how do we differentiate them? E2 reactions require high concentrations. That's not something that usually will show up like on a, as part of a test question. So don't have to stress about that too much. The two things you do need to stress about are strong bases. For E2s, you should read strong bases as charged bases. And then polar aprotic solvent. So those are, so they have like THF, DMF, DMSO, acetone, and acetonitrile, which gets abbreviated MECN. I worked really hard to give myself enough room to make 2 columns, and I totally killed that dream again. All right. So then what favors E1 reactions? Low concentration. Weak bases. read uncharged. Okay, I thought I wrote uncharged on the last one. All right. So uncharged bases, and then polar protic solvents. So that's going to be water, alcohols, and primary or secondary amines. So what I want to do is, some of you had emailed me because you're looking over the old third exams, and we're trying to figure out how I determined if something was a substitution or an elimination. So what I'm going to do is I'm going to skip ahead to slide 12. I will circle back at some point to do the other stuff. But I wanted to do this now so that when you're studying for the exam, today, tomorrow, Wednesday, right, you will know how to do that stuff, so you're not looking at like a third to half of the exam and having no idea what you're doing, right? Because right now, this kind of stuff is a third of your upcoming exam. So I want to make sure you know how to do it and you have time to practice. All right. So let's talk about how you determine substitution or elimination. So if you think about SN2 and E2, they both like high concentrations. They both like strong bases / nucleophiles. They both like polar aprotic solvent. So how do we determine if we're going to do a substitution or elimination? The first thing we can do is we can look at the halides that are involved. Right? The structure of the alkyl halide is going to tell us which of these two reactions we can do. Right? So primary halides mainly do SN2 reactions. If you remember, a primary halide is fastest for SN2 reactions and slowest for E2 reactions. So if given a choice, it's going to prefer to do a substitution reaction. Right? There's one kind of caveat to this. Let's stick with our big bases. So our two big bases, potassium tripbutoxide and LDA, only do eliminations. So if I have a primary halide, sodium hydroxide, and DMF, you are fairly sure that you're going to just do a substitution reaction. If you have the same thing, but you have potassium tripbutoxide, no matter how badly you want to do a substitution, potassium tripbutoxide only does eliminations. It is too big to squeeze down to get to the carbon that has the halide on it to knock that halide off. So it can only do elimination. So even though this is a primary halide, it's going to make a double bond. It's going to do an elimination. So basically, I'd say 95 to 99% of the time, if you have a primary halide, you're going to do an SN2 reaction, right? But if you have one of the big bases, it can't do an SN2 reaction. It has to do an elimination. So if we see a primary halide, you should default to SN2 and then check your nucleophile / base to make sure, right? Then we have tertiary halides. When you have a tertiary halide, you only do E2 reactions. You never do SN2 reactions, right? So if you have a tertiary halide with a charged nucleophile or base, it's a base because it can't do an SN2 reaction. So congratulations, you're making a double bond, right? So for primary halide, mostly SN2. For tertiary halide, always E2. Now, the rub is secondary halides. So how do I differentiate these? So what I do to differentiate these is I use temperature. What I say is that high temperature, which I set to be 20 degrees C and above, that's going to favor an E2 elimination. And then low temp is going to favor SN2. And I set that to 0 degrees C and below. And that's going to favor substitution reactions. So you're going to work your way through, and if you get to a point where you're like tied and you don't know if you're doing an E2 or an SN2, look at the temperature. If it's above 20 degrees, you're going to favor elimination. If it's below 0 degrees, it's going to favor substitution. Now you might be thinking, what about 10 degrees? That is a douche move. I'm not going to give you anything in the gray area. 0 and below, substitution. 20 and above, elimination. No numbers from me between 1 and 19. Not going to do it. Right? So I keep it very cut and dry. What's nice is we can use this same high temp, low temp differentiation for E1 and SN1 as well. So basically, high temperature is going to favor all of our eliminations. Low temperature is going to favor all of our substitutions. So what we should be able to do is look at a reaction and work through it and figure out if it's going to be SN1, SN2, E1, or E2. So let's say we have this. Secondary halide. Secondary halides can do every type of reaction, right? The halide here doesn't really help. So right now I have SN1 available, SN2 available, E1 or E2 available. All right. Now I look at my nucleophile / base. Is that charged or uncharged? Charged. So charge means I get to eliminate the ones. So SN1 goes away, E1 goes away. Now I look at the temperature. Is 30 degrees C above 20 degrees or below 0 degrees? Is 30 bigger than 20? There we go. Yes. So that means we get to eliminate our substitution reaction, and we're doing an E2 reaction here. So we're going to make our double bond, make the most substituted double bond that we can. A very similar format to what is on the test. What is on the test as of this very instant is there's one question, they're going to all be paired. There's one question that is the reaction, that is, tell me if it's SN1, SN2, E1, or E2. Then there's that exact same reaction will be under it with 6 choices for the possible product. And then off of what you've deemed the reaction to be, SN1, 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 SN2, E1, or E2, you should then be able to pick which product you should make. But I'm pairing them all up. That way you have to answer what is the type of reaction and then what is the product. So just like on the practice exam, there was like a box in front that was like, put your type of reaction here. Instead of a box, there's a multiple choice question, and then there's the tell me what the choices are. There are currently 12. So not too far out of range of what is on a normal exam, on like a written exam. It's like exactly the same as like from like 4 or 5 years ago. Okay. This is a tertiary halide, as I almost died. Tertiary halides can't do SN2 reactions, right? So that means, based on the type of halide, that means we're doing either SN1, E2, or E1, right? Is this charged or uncharged? My nucleophile slash base. Uncharged. So that means I get to eliminate E2 as a possibility. And then I have 0 degrees. So the 0 degrees favor elimination or substitution. Substitution. So let's get rid of E1. We're doing an SN1 reaction. Something I want to point out that I forgot to point out earlier is eliminations favor trans double bonds. Because trans double bonds are more stable than cis double bonds, right? They want to make the most stable double bond they can. That extends to being cis versus trans. So just keep that in mind. You want to make the trans double bond if you can. The solvents kind of go with the gosh, what am I thinking? Words. Go with the nucleophile or base, right? So if you're charged, you're in a polar aprotic solvent. And if you're uncharged, you're pulling double duty as either being the nucleophile in the solvent or the base in the solvent most times. So we really can't use the solvent to eliminate anything because they're not independent, right? You're almost always going to see charged with polar aprotic, uncharged where it's also the nucleophile or base in the solvent. So using the solvent is just like using the nucleophile. That's a really big C. So what would my first reaction be? SN1, SN2, E1, or E2? Halide is secondary, so it offers me no assistance. Yeah, I don't know why that's that. Let's make that something that's not dumb. Sorry. There you go. Make that a sodium. There you go, as opposed to a methyl. I don't know. I said in the first class, do you smell burnt toast? Might have an issue. Like 3 people got that smelling burnt toast is a side effect, is a symptom of having a stroke. And the rest of the people I had to explain it to. I was like, oh man. Right. So it is secondary. This is charged. Right? So it's got a metal, so I can eliminate the ones. Minus 20 degrees. Is that cold or hot? Pretty cold. So that means we're going to eliminate eliminations. So we're going to do an SN2 reaction. Can we have the same useless halide that doesn't tell me anything? So, nucleophile, charged or uncharged? Uncharged. So we get rid of the 2's. Temperature, high or low? I'm going to say 60 degrees is high. So we get rid of substitution. That leaves us E1 as our elimination. Make the most substituted double bond. So I will do some more examples on Wednesday and then kind of fill in the stuff that I skipped over to get to here. And then you guys should be good for the exam.